So welcome to the second part of Vladimir's talk.
Okay, thank you. So if there are some other questions, I can start with questions, of course.
Yes, I have this question I wanted to ask. So this, so you have a version of you have your own, in your word, there is a geometric Lagrange kind of statement.
Yeah, kind of. I cannot say that this is the same statement, but well,
No.
definitely it's related, but I don't know.
So this story, the Hecke operators and all that, does it make sense there?
No. For me, it's just some correspondence between two sides. One is Lagrange dual, one is well, affine. But this is correspondence on the level of rather level of cell decomposition than on the level.
Okay. Okay. Yeah. Okay. Thanks.
Okay. So this is my main question, which I address the second part. How to generalize all this business from SO2 to SON to a group G to any group G simple group, finite dimensional. And for simplicity, I'll speak about, today mainly about SLN, but well, what's crucial, not crucial, but well, simplifies a lot. It's just G simply laced. So therefore, we have the object which is chi of the group G, which is the representations of pi1 of the surface into the group G. When I do not indicate the field, I mean that the field is complex, and the question exists always: what is elimination? So I'll start with the definition of high elimination. So what is elimination? Is G elimination. And the first definition existed for many years, but well, we somehow didn't know what is G elimination, but we know what is the moduli space of G elimination. So therefore, since xg is also can be represented, so since kg is a cluster variety, so therefore kg can be represented as with subtraction-free transition functions, free transition functions. Therefore, there is a functions defined over Z, of course, and therefore there exists, one can define chi of chi of Z tropical. And this is by definition can be considered as elimination, which is well, it's moreover one can try, but there is this duality conjecture, which is well, proven in many cases, and this is gives us so well, I just briefly duality conjecture.
Volodya, just a question. So when you say about representing this with this subtraction free transition functions, you're speaking of your coordinates with Goncharov, or like just to be more precise?
Right, mainly. Well, there are some well, for closed surfaces doesn't exist, so there is some version of that for closed surfaces, which is I don't really understand fully. So, well, but essentially our coordinates. so duality conjecture, which is, well, now a precise theorem, but which works in this particular case, and it claims that there is a map. Means that points of chi of ZT enumerate a canonical basis kg of functions on chi g of C, G length dual of C. And this is, well, once again, this is very non-constructive statement. So, well, therefore, it's not very non-constructive, it's constructive, but real computations are impossible because, well, this correspondence starting from point here, construct a function. You need to sum over certain diagrams, which, well, usually there are plenty of them, and it's kind of difficult to compute. Yes.
Sorry for a somewhat provocative question. So here, right, you're telling us there are some constructions, but they're very complicated. Kind of, should we just forget about it and listen to what you will be saying?
No, no, you shouldn't forget. It's really very nice construction. It seems to me it should be simplified in order to write. And I hope that what I'm going to say is one of the ways to simplify this construction in this particular case, because this construction is really universal.
Yeah, we don't forget, but at the moment, frankly, like of this last paragraph, I don't understand much because, right, you are telling us it's complicated and you're not telling us what it is. I mean, maybe instead we should listen to your simplified construction already, right?
Of course. Yes, for today, you can forget about this construction. Definitely, but it's a beautiful construction. I don't want to say that. So I would like to have something more geometric. So, like for example, this well, trace of monodromies, which are something which is very easy to compute, and you don't need to sum over something. So this one thing. But well, once again, maybe, well, it's I will not give the answer to this question today. So this is another thing. But what I want to say that I want to nevertheless to give a definition of lamination, which is just generalized lamination and definition. Generalized lamination. And this will be the following object, which is now it's not longer. Well, I'll give a definition and then explain how it's related to all this business. So it's a graph with edges colored by elements of by simple roots of the affine group, which is the same thing as generators of the corresponding Weyl group. So it's the same set. For example, which is which will be example, if G equals SO3, so you have three colors, which will be red, green, and blue. Well, there are three generators. There will be three colors, and I'll imagine them red, green, and blue. So these are simple roots, and there are edges connecting them in the Dynkin diagram. So it's a Dynkin diagram, and then the graph is generated by that, and then the relations, well, with some conditions. So the graph has three types of types of vertices. So if you have two colors, which is SO3 such doesn't exist. If you have two colors, I'll call this A and this I call B. Then I have a 4-valent vertex if the colors are related by are not related by if CAB is equal to 0. So if they are not connected.
Sorry, Vladimir, what is it that you are coloring? Is it the edge or the vertex?
No, I color me edges, and this is just a Dynkin diagram.
Oh, I see. Okay.
It's not this graph.
Okay.
No. Sorry, this is just I mentioned that there are Dynkin diagram with vertices colored by that, and out of the Dynkin diagram with colored vertices with different colors.
Okay.
I draw a graph. So if the roots are not connected, I allow just a simple intersection. If the roots are connected, like for example red and blue, I allow the vertices of this type. So this is A. This is B. If CAB equals to -1, so if the vertices are connected, I have these 6-valent vertices, and also there are kind of we'll see that there are only finitely many of them, so we can also have just simple trivalent vertices. The same. So there are 3 vertices, and there are relations between and also this graph up to relations. So it means that some certain graph are equivalent up to, of course, we consider up to isotopy, but also up to certain relations, which is some list of them. And currently, there is one relation which is this one is equivalent to this one. The closed loop is equivalent to just the empty set, and there are some some relations which are some relatively obvious if I have 3 colors which do not which are not related at all. I don't know. Well, these 3 colors means that, of course, these are the Meister 3, which if the colors are not connected, you can just move freely the edges. For example, something like that.
Volodya.
Yes.
A stupid question. So how does it all play in the simplest case of SO2, right? You're now outlining a little bit how it works in SO3, but just right, it should specialize probably to the previous pictures for SO2. Maybe you can briefly say how it...
And maybe I should it's just some picture which I can draw, but maybe plus some relations which I plus some relations which actually borrowed. It's not our relations. We try to figure out all the relations, but it turned out that all the work is already done, but from Ben Elias and Williamson. they have a beautiful work about representations, about, well, the Zergel bimodals, the morphism between Zergel bimodals, and turned out that the relations we need exactly the relations from their paper. So this is a kind of, well, I am trying to study their paper, and it turns out that one can marry the two approaches, because they ask completely different questions. They ask questions about Hecke algebras also, but it's completely different. And now the good question then for SL2. So for SL2, the idea is the following. So suppose you have a surface which is, well, you have a collection of, as before, you have a collection of curves on the surface. And out of that, you can construct a, well, for example, you can construct a bicolored graph, and the bicolored graph looks the following. Imagine that you cut your surface by these green lines. So what's remaining, except for if it's empty, what's remaining is just a collection of of pair of pants, and every pair of pants you fill with well, or maybe other surfaces, but definitely the surfaces which can be retracted to a graph. And so you just draw this graph where what the surface can be retracted to on this surface. So we have the graph where green lines are well, just circles, and red line. Sorry, and also, of course, if you have double lines, here you have double lines. It corresponds to cylinders, and if you have cylinder, you just take a closed red line. And the result, if you apply this relation, for example, the results are not unique, of course, because you can draw. Well, for example, if you have a surface, well, if the decomposed surface a little bit more complicated than pairs of pants, so in this case, you cannot. The red graph is not unique, but different red graphs of this type can be obtained one from another by this relation. So this is the same thing. So from ordinary lamination, you can construct the high lamination. And this is just now I want to, so this is a, well, relation. So now another property of this lamination. So it corresponds to the property, the last one, which I talked about, the higher laminations. You can have a correspondence. Higher laminations which correspond to cells in the following space. So you have your group G. Well, but maybe it's better to take it on as dual to yes. And you have the group GL, and you take the character variety, so representations of pi of the surface into GL of hat. So how to do that? So if you have if you have eliminations, we say that a high elimination So this is a representation. This is, I imagine that as a flat connections or local systems. Flat connections, maybe flat connection, flat GL hat connections. For simply laced case, well, there is a difference between GL and G, but this is not well. For a moment, I just well, for simply laced case, the difference between GL and G is not very strong. So here you can ignore it for a moment. So we say that high lamination is compatible with with a flat connection if one can choose a covariantly constant flag above each component, each face of the graph, in such a way that the idea is following. So if you have a face of a graph, which is just some multicolor object, I don't know, I draw something like that. The idea is that you have whatever you choose flags F1, F2, etc., F3, and we know that the flags, if you have the space of flags F, well, the remark, which is very simple, that you have G hat quotient by B hat from left and right. There is a very easy statement that it is isomorphic to G hat quotiented by B hat squared quotiented from the left by G hat. This is a statement which is true for just any group and subgroup. It's not about G hat and B hat. Just you have a group and subgroup, the double quotient from the left and right is the same thing as a single quotient from the right, squared by G from the other side. So this set can be imagined, the space of G hat quotiented by, or G quotiented by B from the left and right. You can imagine that as just as pairs of flags quotiented by the action of the group. And so therefore, in a sense, if you have two flags, then you have the map from the space of G hat by B hat squared. You have a map from that to the value group hat, of course. And what I want that this choice of these flags should be such that if you have an edge of the type given by the generator of the flag, so this means that you have F1, F2, you have an edge, you have here F1, here you have F2, then F1, F2 is mapped, and here we have element A of your while group, so generator A of the while group, so the F1, F2 is mapped exactly to A. So it's a collection of flags which is compatible in the sense with this edge. And so therefore we get for every, so this is the claim. And actually this claim is also partially borrowed from the paper of Anton Mellet. Is that for a given graph, given high laminations, the set of set of compatible flat connection is a cell.
So which paper is it?
Very good question. He sent me a PDF file of some of his paper, but and we discussed it with him by email. So this is well, I will send you the reference. Sorry, I don't exactly remember.
Maybe I have an easier question. What does it mean it is a cell?
Cell, in a sense, well, the product of C star.
You can introduce a coordinate chart in what,
there is a
right.
coordinate chart. Once again, I would like to do it in cluster way. Anton introduced the charts which are not cluster. I didn't understand quite well the construction, but well, they definitely it's product of C and stars, C and C stars.
Okay, I know which paper it is then. So.
Yeah. Now the well, what is amazing also about this especially in Melick's context, he didn't consider the connection in affine group. He considered connections in finite dimensional group, and actually these constructions are compatible. So therefore, if of course among all laminations you can consider, so there is a space of lamination, higher laminations LG. And there is this subset of sigma, and there is a subset of L0G, which is just graphs with edges which enumerate doesn't contain one color, which with colors by simple roots of G. And this, well, there are finitely many of them. So finitely many, and it gives a decomposition, a cell decomposition of ordinary space. Cell maybe I'll put into of the ordinary just representations of G, pi 1 to G. There are finitely many of them, pi 1 sigma to G. So there is a byproduct. Maybe I should. Yes, this is well. I have not such much time. So second remark that well, this is a relation to the cell decomposition, which is kind of yeah. This corresponds to this well Satake correspondence, but in the more generalized way. So I want to say that this L0G also one can consider as a map. So if you have a high lamination, there is it gives a map pi 1 of sigma minus triple vertices to the Weil group. Indeed, if I have a surface and I have a graph, so triple vertices are really kind of distinguished. I have a multicolored graph. So I can have triple vertices and I have sextuple vertices. and quadruple vertices. Sorry, no. Sorry. Every time if I have a path on the graph, then every time I go around triple vertex, I have non-trivial, so we have three generators. So this path corresponds to the product this path corresponds to the product of AAA. If I have AAAC, so it corresponds to A cube, which is just A. But on the other hand, if you have the vertex which is 6-valent, then the product with A, B, A, B, A, B, no, A, B, A, B, A, B, then this path gives me A, B, A, B, A, B, which is trivial. And therefore, well, if we forget about 3-valent vertices, then we have this homomorphism. So it's in fact this is kind of W hat. Sorry. This is kind of correspondence. So you can imagine high lamination not as a graph, but as a kind of it's a curve. So a covering of your surface with, well, what's covering? Usual covering of the surface is a map from pi1 of minus ramification. So covering is a map from pi1 minus ramification points to the symmetric group. So it's kind of generalization of the notion of the covering. Then you cover with a surface which is, you replace Sn by some affine Weyl group. Or other point of view on the same thing, that you can imagine that, well, for SLN, there is a correspondence of high laminations and covering. Well, I'll minimal coverings with sigma tilde to sigma with a form alpha belonging to just closed form, well, homology class actually, belonging to H1 of sigma tilde. Maybe I should also, for if I want SLN, then I question it by H of sigma with values in integers. One of sigma. This is not very important as an element. So I claim the following, that so this is a spectral curve, but spectral curve is understood in a very rough sense. So it's not longer a complex curve, but just, well, if you have a covering equipped with one form which is closed, then it gives you a curve. So it gives you an embedding of your curve sigma tilde to just T star of your curve, just by definition, or other way around. If you have an embedding of the covering into, if you have a curve in T star of sigma, which recovers the curve sigma, so the same thing as just covering equipped with one form. this gives you a map from if you have a path on your surface, so you have a surface and you have a path on the surface, then for this path, this is the path gamma, for this path, for every point of this path, you can associate a collection. Well, you have, for the path gamma, you can associate an integral of alpha with respect to the path, the preimage of the path gamma. So this is a collection of n points in R over Z. And therefore you have a collection of points. So, so this is a collection of points on a circle. And well, we know that the collection of points on the circle is well, the W hat, well, SLN hat, for example. I am speaking about SLN now. SLN hat is equal to the well, one can imagine SLN as elements of SLN. It's a diagram of the type that you have cylinder and you have points which move along the cylinder. Well, the element of SLN is just this picture, and we can reproduce this picture if you have a covering of a surface and moving, covering of a surface with form on it, you get an element of W, and this gives you a high lamination. This setting. So this is a just maybe, well, I have do not go into details, but the idea is that this correspondence, which is quadratic differential, gives you ordinary lamination, can be generalized for this case. The one I would like to say, well, I have not much time, but I have want to say one byproduct of all this story, and the byproduct is the following. So if you have, we can well, remark, which is well, the byproduct is some kind of topological quantum field theory, which is can be constructed out of these high laminations, which I never met, but it's so obvious that it should exist somewhere. So if somebody seen it, it would be nice. So the topological quantum theory is the following. So if you have a well, you have your Hecke algebra, finite dimension. If you take a finite dimensional Hecke algebra, G and the Borel subalgebra, so this is the algebra generated by S alpha with all these relations, and it's just it's generators. But on the other hand, what I said recently, so this is the same thing as a well, is a function of as a vector space is isomorphic to C of the Weil group. So you have generators in this algebra, which is the same as the Weil group. So we have traditionally the generators are now these are generators of this space as a vector space. So they are called TW, and you have of course you can easily compute using relations. You can compute the TW prime. This will be some structure constants of this algebra. So it's TW W prime, W to prime, TW to prime. There are some constants which you can compute in this way. Well, these constants are not cyclically invariant. So remark, if you have if you have TW tilde, which is equal to TW times Q to the power minus length of the W, and you compute the tilde's constant, TW prime, tilde, TW2 prime tilde, then these are cyclically invariant. Constants. Now, the claim is the following, that if you have a surface, you have a triangulated surface, then you can associate to it a polynomial in Q. So how you associate? You take the triangulated surface, and this P of Q, which will be the sum, well, this standard partition function. So you take the elements of the while group on the edges.
So sorry, Volodya, possibly
Yes.
stupid question. Are you getting now to QFT? Because when you have cyclic symmetry, you have some kind of Frobenius algebra, or is it?
Yeah, it's a Frobenius algebra. It's non-commutative Frobenius algebra. Yeah, of course, it's nothing but that. So you have a sum of C, Wi, Wj, Wk over the triangles. But well, W is actually associated to oriented edge, so you need to orient the edges, and every time you change the orientation, you need to replace W by W inverse, and you can compute a polynomial. Of course, if you have instead of that, you have a polygon, for example, which is triangulated, then you get a polynomial which depends on Q, but also depends on external edges. So you have W2, etc., Wn, which is also a polynomial, and the claim is the following: that this polynomial P of Q, W1, etc., Wn is the following animal. So this is Q minus. First of all, well, this is a polynomial with positive coefficients, integral coefficients, which of course we don't need to know how to prove. Though we might work about this subject, but it's equal to the following object. So it's Q minus 1 to the power of number of triple points. So it's a sum, sorry. It's a sum over all high laminations. Q to the number of triple points of Q minus 1, sorry. To the power to the number of triple points. So therefore, for example, we have for example, the structure constants of the Hecke algebra itself can be computed in this way. Just an example, so we want to compute CW0, W0, W0. So W0 is equal to ABA. So this, what we do, we just draw a picture like that. And when we need to connect these, well, we have, for example, So there is this picture, or there is another picture which contributes another term in this. So you fix this picture contributes q to the cube, q to the q minus 1 cubed. This contributes q minus 1 for first to the power 1, and so this is actually the only situation. Then the structure constants is given by two different diagrams. So this is and well, this counting the high laminations is the well, it's some problems which arises in different possible ways. And another conjecture which we don't well, formally, if our conjecture is true, then it is should also be true, but we didn't reproduce it. That if you have if you work in triangle, so you can consider high laminations on a triangle, you fix the elements of the wide group on the sides, which are elements of the higher. Well, maybe I should just mention that that the Littlewood-Richardson can be computed numbers can be computed as number of high laminations on a triangle. So in a sense, yes, this is another statement. So well, maybe I stop here so I can. Well, there's a main places. I tried to list it, main places where high lamination intervene, and well, make some commercial of that. Okay, I stop here. Sorry.
Okay, well, thanks a lot for your talk. So are there any questions? Please, kind of remote participants, raise your electronic hands, or participants on site, tell me if you want to ask a question. In the meantime, I can start with my questions, and then you kind of you think and tell me. But so one naive question I have is as follows. In the first part of the talk, you remember there was this one form alpha, and you constructed it as a square root of t of the quadratic differential. And then
Right.
you also mentioning in this high lamination story, there was also the form alpha. But do you relate it to some higher order, whatever, 3 differentials, 4 differentials, and so on? Is there such a thing? Yeah. So I now mute myself and.
Yeah. Right. Of course. So there are if you have a surface and if you have a surface and the collection of differentials, so I don't know, T2, T3, surface means the complex structure, mu, and T2, T3 homomorphic, Tn is homomorphic, and differentials, then you can construct the form alpha, which is just a solution of the equation alpha to the n plus T2 alpha to the n minus 2 plus etc. plus alpha n plus t to the n, tn equals 0. And the solution alpha is a one form. And therefore, we have alpha is one form, one differential, and the real part of alpha is h1 of sigma tilde, where sigma tilde is Riemann surface. Well, it's n-valued. Well, alpha takes n-valued at the point, so you have a covering, and therefore you have a map from collections of differentials T2, etc., Tn. And here is a complex structure plus collection of differentials. You have a map to H1 of sigma tilde. But the main difference between the two dissipation of SL2, SLN, so that this is not isomorphism. For example, the dimension of this space is much lower than the dimension of this space. And the idea is that how you can get around. So instead of considering, well, using complex structure and holomorphic differential, you get only part of this space. You really need the whole space. So instead of considering the curves which are obtained in this way, you consider all the curves. Well, this sigma tilde, well, sigma tilde is embedded into H1 of is considered is T star of sigma tilde, T star complexified, T star complexified of sigma. So this is a spectral curve which is holomorphic. So instead of considering holomorphic curves, you can consider, so it's holomorphic in this particular case. So you, instead of holomorphic, you consider, you replace holomorphic by Lagrangian simply. And if you allow yourself vary the curve inside among all possible Lagrangian curves, you can compute much larger space. And so therefore, well, for me, for example, I need to, the main problem with holomorphic curves that unfortunately they very seldom belong to H1 of sigma tilde with value in integers. Because for SL2, there are, because just this is an isomorphism and there are quadratic differentials and complex structures correspond to integer forms. But for higher genera, for higher group, this is, well, hit an integer is, well, almost improbable. But if you allow yourself the generalized spectral curves, which are not holomorphic, but only Lagrangian, that you get every curve and everything is fine.
Okay, thanks. More questions? So raise your hands or tell me. I got one more question. In the meantime, so you mentioned this Littlewood-Richardson story, right? So those higher laminations give some kind of categorification, right, of Littlewood-Richardson. But then we know that there are all those whatever honeycombs and some other combinatorial ways. And they also in some way honeycombs, they're in some way associated to a triangle. So how are those stories or whatever hives, honeycombs, how are those stories related to higher laminations?
Right. Well, this is thank you for this question. It's well, I cannot give the answer in the sense of algorithm, but ideologically, it's clear how it happens. So, for example, if you have a honeycomb or hive, it corresponds to the following. So you have some picture like that, and you have well, numbers on faces of this on this hive. And you interpret these numbers, I don't know, some numbers as, well, for example, as monodromy around, you have the number x, so it means that you imagine that on your graph, you have a graph connection, just abelian connections with values in Z. And you have just, well, Z or, yeah, and you have this X is just monodromy of your graph connection. So you have, so hive, for hive, you can construct a connection on gamma, on the graph gamma, which I drew here. But on the other hand, this graph gamma is embedded into the spectral curve. So the spectral curve is just purely combinatorial object. So there is a so you have a surface which is just a covering of your triangle, and which is ramified in just 3 points. And this graph gamma is embedded into the surface, and therefore, well, in this particular example, it's 3 points. In general, is ramified in every this black vertex. So therefore, if you have a connection of gamma, then it gives you connection on of one form. You can consider, well, elements of H1 elements alpha, which is in H1 of the surface sigma tilde, and out of that you have a lamination, higher lamination. So this is a well, on the level of drawing picture is not clear. Yeah.
So any further questions or comments? Yeah, Jan. Yeah, maybe first Jan and then Tamas. Yeah, because we already have this mic switched on.
So is it easy to see how to get from this graph, which is decorated by the generators of W hat, a function on the character variety?
Yeah, thank you very much for this question, but well, the answer is no, it's not clear. There are some very complicated suggestion by Vladimir, but well, so far we have no answer for that. Yeah, this is, well, I would rather say that.
Okay,
we
thank you.
It's a very natural question.
Yes, I don't know if this showed up for you, maybe not because you haven't mentioned, but the Kohomology polynomials are closely related to the Hecke algebra and the geometry of cell decomposition in the Schubert variety in the affine Grassmannian. Did you see anywhere in your work
yeah, well,
Kohomology polynomials?
Definitely I expected this question, and we are thinking about that. The answer more or less the same as a previous question. So you can pass to the basis of Kohomology polynomials, and it gives you some bases which are not by high elimination, but certain linear combination of them, which have some very nice coefficients. But so far we have no idea what geometric meaning of Kohomology, though we tried to find them. It should be really, well, I think that after reading attentively the paper of Ben Elias and Williamson, we could give you an answer for that, but well, it takes some time.
They have, those things show up for them, right?
Yeah, for them it's for them the natural basis is Kohomology basis and not the W basis.
For the affine Hecke algebra, I mean for the affine Y group as well.
For both for affine and finite dimensional, for them it's the same. The difference, the only thing there, well, for example, this topological field theory, it doesn't work for finite dimensional affine Y algebra because the sums are infinite. But on the other hand, for example, we use this to show that for triangle, one can show that for triangle, even for a affine group, the number of ramification points, namely the triple verses, is always finite. As a theorem by Lustig, well, translated in our language. And so.
Okay, thank you.
Okay, thanks a lot. Any more questions, either here in the Diablerie or remote? Well, if not, Valore, thanks again.